19.4. Work in thermodynamic processes. In this session, we will explore the fundamental principles of work within thermodynamic systems. We will begin by distinguishing between state variables and transfer variables to understand how energy moves. From there, we will examine the specific mechanics of work done on a deformable system, such as a gas contained in a cylinder. We will also learn how to use pressure-volume diagrams to visualize these processes and see why the work performed depends on the specific path taken between states. Finally, we will tie these concepts together using the first law of thermodynamics, which serves as a specialized version of the law of conservation of energy. To understand thermodynamics, we must categorize the variables we use. State variables describe the current condition of a system, such as its pressure, volume, temperature, and internal energy. These values can only be clearly defined when a system is in internal thermal equilibrium, meaning every part of the gas is at the same pressure and temperature. On the other hand, transfer variables like heat and work only appear during a process where energy moves across a boundary. These variables are associated with the change in the state of the system rather than being a property of a specific state itself. You can think of state variables as a snapshot of the system, while transfer variables represent the action of moving from one snapshot to another. Let us look at the mechanical work done on a gas. Imagine a gas inside a cylinder with a movable piston of a certain area. The gas exerts an upward force equal to the pressure times the area. If an external force pushes the piston inward by a small vertical distance, work is done on the gas. We calculate this small amount of work as the negative of the force times the displacement, which equals the negative of the pressure times the area times the vertical displacement. Since the area multiplied by that displacement represents the change in volume, we can simplify this to say that the work done is equal to the negative of the pressure times the change in volume. This relationship shows us how mechanical movement directly translates into energy transfer within a gas. The sign of the work done is very important and depends on whether the gas is being compressed or is expanding. During compression, the change in volume is negative, which makes the work done on the gas positive. This means an outside agent is putting energy into the system. Conversely, during expansion, the change in volume is positive, making the work done on the gas negative, indicating the gas is doing work on its surroundings. If the volume remains constant, no work is performed. To find the total work done during a change from an initial volume to a final volume, we calculate the negative integral of the pressure with respect to volume over that range. This requires us to know exactly how the pressure changes as the volume moves. A pressure-volume diagram, or PV diagram, is a vital tool for visualizing these thermodynamic processes. On this graph, the vertical axis represents pressure, and the horizontal axis represents volume. A curve or line on the diagram represents the specific path the system takes between its initial and final states. Based on our integral definition, the work done on the gas is equal to the negative of the area under this curve. In the example shown on the slide, the gas is being compressed from a larger initial volume to a smaller final volume. The shaded region represents the magnitude of the work, and because the volume is decreasing, the work done on the gas is positive. One of the most critical concepts in thermodynamics is that work is path-dependent. This means the amount of work done depends on the specific sequence of steps taken to get from point A to point B. Looking at the three graphs, we see different ways to reach the same final state. In the first path, we compress the gas at a constant low pressure and then heat it at a constant volume. In the second path, we first increase the pressure at a constant volume, and then compress it at a high pressure. The area under the second path is much larger, meaning more work is done because the compression happens while the gas is at a higher pressure. A third path shows an arbitrary compression where both pressure and volume change simultaneously. In each case, the work is different, even though the starting and ending points are identical. The first law of thermodynamics is essentially the law of conservation of energy applied to thermal systems. It states that the change in the internal energy of a system is equal to the sum of the energy transferred by heat and the work done on the system. Mathematically, the change in internal energy equals Q plus W. We specifically use the notation for internal energy to avoid confusing it with potential energy. This law tells us that there are only two ways to change the internal energy of a system. You can either transfer heat across the boundary or perform mechanical work. It provides a complete account of all energy entering or leaving a system during any thermodynamic process. To summarize our key points, we have defined the work done on a gas as the negative integral of pressure with respect to volume. We have seen that work is a transfer variable, meaning it is not stored by the system, but describes the process of energy movement. Because work is path-dependent, the specific steps of a process matter, and this is visualized as the area under the curve on a PV diagrams. Finally, the first law of thermodynamics provides the governing equation relating the change in internal energy to the heat added and the work performed. Together, these concepts allow us to track energy flow in any deformable system undergoing a change in state. To wrap up, consider these review questions to test your understanding. First, why exactly do we classify work as a transfer variable rather than a state variable? Think about the requirement of being in a specific state versus undergoing a process. Second, if a gas expands slowly and steadily from an initial volume to a larger final volume, will the work done on the gas be positive, negative, or zero? Use the integral definition to justify your answer. Remember to consider the sign of the change in volume and how that affects the final calculation of work.